Hi, welcome to the last lesson of this week, lesson 4 for this week, carboxylic acids and esters. We're going to be learning about other organic compounds that are made of carbon and hydrogen, but with some other elements in there as well, hence they are not just hydrocarbons. But before we do, I want you to do a retrieval task, just reminding yourselves on how to go from the box on the periodic table, like the one you've got in front of you, and turn it into the full electron diagram, the structure, and we're going to do sodium. So you need to remind yourself which one of those numbers you need, and then how to actually draw the electron structure, so the diagrams with the circles and the crosses for sodium. So pause the video now, draw that, and then we will go through it. Okay, so let's check our answers. So first of all, we should hopefully all be aware that the bottom number, or the smaller of the two numbers, is the number of electrons. It's also the same as the number of protons in an atom. So we've got 11 protons and 11 electrons. So we're going to draw the electron diagram. Now, remembering that the first shell can only hold 2 electrons and subsequent shells can hold 8, we put 2 in the first shell, 8 in the next shell, and then 1 in the final shell. Now that first shell, ideally, the electrons would be opposite each other rather than next to each other. But the main thing is that you get the right amount in each shell. And focusing on that second shell, that you can see that they are paired up. So you go round like a clock and you fill up once, and then you go round and fill up again. So you'd put 1 at the top, 1 at the 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And then once you've got the first ones in, you then pair them up. So go round again. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. You would then have 10. That shell is full. So you go to the next shell and it goes at the top. So hopefully you got that right. If you didn't, we will do some more practice. It's one of the fundamental things you need for your chemistry. So it's good to just keep reminding yourselves on how to do that. Definitely copy the diagram down if you got it wrong, and look for where you got yours wrong. But I think generally it's the main thing is you remember that the second and subsequent shells have got 8 electrons in, and that first one only takes 2. So on to today's lesson, we're looking at more organic compounds, and we're going to be exploring the reactions of these two new compounds, carboxylic acids and esters. So the first thing we're going to do is we're going to look at the functional groups, and remember that's the part of the compound that makes it behave the way it does. So we're going to draw some carboxylic acids, just as we've done with alkanes, alkenes, alcohols. We're going to draw the structures out. And then once we've done that, we're going to describe and explain the properties and uses. So carboxylic acids, how do they behave? Why do they behave like that? And therefore what we can do with them. And then we're going to explain them from them, very similar for esters, but also a very important thing is how you name an ester. So that's what we're going to be looking at. The main part of the lesson is how you construct an ester, where they come from, what you use to make them, and then therefore where the names come from. So I like this lesson, it's really interesting. Lots of drawing of displayed formula and things like that. So let's get cracking. So we've talked about functional groups a little bit before. So if you look at the left-hand side, carboxylic acids, so for example, ethanoic acid, the names will always end in oic. So oic acid, so ethanoic acid, propanoic acid, and so on. Now, if you look at the diagram above it, you can see that you've got your I, and remember that's any basically alkane, and so the last hydrogen is replaced with this structure. So this is what makes something a carboxylic acid. So you've got that last C has got a double bond O and then an OH as well. So you've got this COOH, and that is your carboxylic acid. Now, if you look on the other side at an ester, so when we name esters, they'll always end in -OH, so e.g. ethyl ethanoate, and we're going to look where those names come from a little bit later on, because it's quite interesting. And if you look, it's very, very similar to carboxylic acid. The only difference is, instead of having that OH, that H is replaced with another alkane. So you take that hydrogen off the alkane and pop it on the end. So it means they behave very differently, but they're created basically from carboxylic acids, and you're going to look where those come from in a little while. So focusing at the start on carboxylic acid, so our functional group is this COOH, and any names will be anoic acid. So for the first one carbon atom, so anything with one carbon atom will be meth. So we've had methane, we've had methanol, and now we've got methanoic acid. So you can see that the carbon atom still has 4 bonds. It will still always make 4 bonds. So you can see the 4 lines coming out of the central carbon. So you've got your C double bond O and your OH, and then to make sure you've got your 4 bonds but no additional carbons, that other bond is completed with a hydrogen. So methanoic acid, and when we write the structural formula, we put it in the order that we see it. So just like we did with the alcohols, it helps us to understand what it actually looks like, how the elements are arranged. Because technically we could write CH2O2, because that's still the same. But it doesn't help us to understand that that is methanoic acid. We wouldn't be able to see the COOH, which we are going to come to recognise as the carboxylic acid. So if we look at ethanoic acid, so you can see there, the first thing you always draw, if you were to draw these and construct them, which you're going to have a go at in a minute, always put your carbons in first. Now, F, we know, ethane, ethene, ethanol, 2 carbon atoms. So that's the first thing that you must draw. So ethanoic acid, 2 carbon atoms. On the second one, on the second carbon atom, or the last one, if you've got more, put to the side the C double bond O and the OH, and then you fill up with hydrogen atoms so that you've got enough bonds, you've got 4 bonds coming from each carbon atom. So this would be ethanoic acid. And if you look, we've still, at our structural formula, we've still got COOH on the end, but that's attached to a CH3. So it just allows us to see how it is arranged. We've got a CH3 with the COOH attached. Now that's ethanoic acid because, so it's S because it's 2 carbons, and it's anoic acid because of the COOH. So what I want you to do now, I'm just going to pause for a few seconds, and I want you to consider and try drawing propanoic acid. So prop means 3 carbons, so prop means 3 carbon atoms. So I want you to now look at the other 2. You've got to have the COOH. You've got to have 3 carbon atoms. And I want you to have a go now at drawing that. Okay, so let's have a little look and see how you did. So the first thing you do, you put your 3 carbon atoms in the middle, and on the last one, you write your COOH, and then you fill up with hydrogens. So hopefully you got this diagram. Now what I want you to do while I'm talking is I want you to write down the structural formulas, the letters. So write its name and then write the structural formula using the other 2 for help on looking at that diagram. Okay, so you should know that we've had methanoic acid, ethanoic acid, so the next one must be propanoic acid, remembering most elephants prefer bananas, so we're up to P, so propanoic acid, and the structural formula, if you follow it along like a bit like a map, so at the start you've got a CH3, the next thing you've got is a CH2, and then you've got your COOH. We will write that down on the next slide. So all we're going to do is condense this information into a table. So what I want you to do is draw this table out and condense all that information, so all the names, structural formulas and the displayed formulas, so basically draw them out nice and neatly so that you've got it in one simple place that you can just refer back to. So pause the video now and then we'll go through the answers. Okay, so we're going to go through these. Obviously, the first ones were done for you. And we're going to have a look at the next one. So we said the next one was ethanoic acid, CH3COOH, making sure that you know there's no more than 2 carbon atoms. So always make sure of that. And that's your structure: 2 carbon atoms, C double bond O, and OH on the end, and a CH3 to start off with. So the next one was propanoic acid. So we said, here's the structure that we didn't have on the last slide: CH3, CH2, COOH. Kind of make sure as well that you are putting those little numbers down at the bottom. They're not the same size, they are not up at the top like it's cubed or squared. They must be written like that, because if they're not and you get a question on it, you will get the question wrong. It's very, very strict. If they're the same size, or they're up at the top, or they're in the wrong place, it's wrong. They've got to go there. So there's your structure: 3 carbon atoms in a row, you C double bond or OH on the end, and filled up with hydrogens. So lastly then, the one that we've not talked about, so we can see most elephants prefer bananas, which make it butanoic acid. So it's very, very similar. Now, the structural formula, all we do now every time is we add a CH2 to the middle. So we've got CH3, CH2, CH2, and then COOH. If you were to go on to the next one, and it was pentanoic acid, that structural formula would be exactly the same, apart from you would have another CH2 in the middle, and that continues every single time, because that's how you're making a CH2 would ensure all the carbons have 4 bonds when it's attached to the others. So lastly then, 4 carbon atoms in a row. The last carbon atom doesn't have the hydrogens attached, it's got your C double bond O and your OH, and all the others are filled up with hydrogens. If you did get any of those wrong and you're unsure why, do send me an email so that I can help you out with that. But just make sure the key thing is that you've counted that each carbon atom has 4 bonds, and that last one, and this hopefully would be what you drew in after you drawn your carbon atoms, is the first thing you put in after your carbons is the C double bond O and the OH, and then after that it's just hydrogens, making sure that every carbon has 4 bonds. Wonderful. So once you can do that, the rest of it is pretty easy, because the final criteria that we're going to move on to is basically drawing those plus the alcohols that you did last lesson and putting them together. But before we look at that, we're going to look at the properties and why they behave the way they do, and then from that, what we can actually use them for. So carboxylic acid. So we've got a nice simple one there. We've got ethanoic acid at the sides, because we can see 2 carbon atoms, and we've got a beaker of water. Now, just like we looked at with the alcohols, we're doing the same. So they will dissolve in water. They won't create 2 separate layers. They will dissolve. The only thing is, where alcohols dissolve to make a neutral solution, these dissolve to form an acidic solution. Not really surprising, considering they are carboxylic acids. So when they dissolve in water, they form an acidic solution. Now, there's a YouTube link there that you won't be able to click on, but I've also put it in class charts, and it's on the PowerPoint that's in class charts, so that you can click on it, and it's just general information about carboxylic acids and esters and where they get the names from, which is what we're going to look at in a little bit. So it might be useful after you've done this PowerPoint to go through and watch that. Now, like any other acid, they behave similarly, but there are some differences. So it says, what do you observe when HCl, hydrochloric acid? I'm hoping that you can recognise that HCl, hydrogen and chlorine, is hydrochloric acid. We use it in the lab all the time. So what do you observe when hydrochloric acid added calcium carbonate? Now, calcium carbonate is a little white stone. It's basically sometimes labelled marble chips. It can be labelled limestone. It can be a powder, it can be big chips, it can be large chips. When you do rates of reaction, you use this reaction a lot. So when you add an acid to some calcium carbonate, what is produced? What do you observe? Now we observe a gas. That's why we use it for rates of reaction, because we can measure how quickly that gas is produced. Now, When we add something like ethanoic acid, so a carboxylic acid, if we add that to calcium carbonate, they behave similarly in that you get a gas as well. However, the reaction is much slower. The acids aren't as strong. So the pH isn't as low. So if you added universal indicator to it, it wouldn't go the bright red that HCl would. It would be sort of a yellowy orangey colour, not as strong an acid. Now this gas, anytime you add an acid to a carbonate, you always get carbon dioxide. So that's just good to know for quite a lot of different topics, especially rates of reaction, but for this one as well, you will look at that reaction quite a lot. But anytime you've got a carbonate and you add an acid to it, you will always get carbon dioxide gas from the carbonate. So what we can take from this is that ethanoic acid or all carboxylic acids react slower than something like hydrochloric acid because they are not as strong. So the pH would be between 2 and 5. We're not getting as strong as pH 1. So let's have a look at this in action then. So if we add, that's ethanoic acid, to our calcium carbonate, that's a powder, it would start to dissolve as it reacted, it would get smaller, and you would get carbon dioxide gas like we've said, and you would get water and the salt. So carboxylic acids react with carbonates to produce CO2, H2O and a salt. Now a salt is just the name of a compound and it would depend on what carboxylic acid you've used as to what salt you would make, but salt is just the general name of the product. And it would be dissolved in water because that water, they don't separate. The carbon dioxide is given off as a gas and then the remaining solution would be your salt dissolved in that water. So you probably didn't know this, but ethanoic acid, which is the most common carboxylic acid that we might encounter, is actually the acid that's in vinegar. So you are technically putting on your chips ethanoic acid. Now some people call it acetic acid. That's just the proper chemical name. Ethanoic acid tells us its structure because we know anoic acid means it's got the COOH. We know the F bit means it's got 2 carbon atoms. Lots of things in science have separate names, have other names, just general names. So acetic acid is the general name for it. Ethanoic acid, its proper name, helps us to know its structure. So why do they make the solution acidic? So in there you've got some water and you've got some carboxylic acid, you've got some ethanoic acid. Now they behave in the same way as any other acid and why they become acidic. Because what happens is, as you can see from what's just happened in the animation, the hydrogen separates, it's what's called dissociates. So it pulls itself away, the water allows it to separate from the rest of it. Now, hydrogen ions always have a positive charge, which means the remaining compound or ion is negative. So it's the H plus ions in the solution that make something an acid. Now, this is the bit that's on higher tier. Now, when you do a different topic, when we're talking about the reactions of acids and alkalis, this is really important for this as well, knowing why something's an acid, not specifically carboxylic acids, but knowing what a strong acid is and what a weak acid is. So it's good crossover on the topics here. So if we look, there we've got 3 different molecules of our ethanoic acid. Now, obviously, there would be millions of these, but what we can see is that not all of the carboxylic acids dissociate. They don't all ionize, so where they basically turn into an ion. Not all the hydrogens on the end of the COOH will become separate. And that's what makes it a weak acid. Something like hydrochloric acid, every single hydrogen and every single chlorine ionize, they separate from each other. So that makes something a really strong acid. But when ionization isn't complete, so it doesn't happen to every one of the molecules, that means something is a weak acid. It's only partially ionized. So just to make sure you know the difference between concentration and strength. So strength is all to do with pH. Okay, so pH, a strong acid has a pH of 0 or 1, and a weaker acid has a pH of 2 to 6. It doesn't mean that there's a different concentration. They could both be 1 mole on 1 mole per decimeter cubed, whatever unit you want to use. It just means that one is more acidic than the other. One would ionize more completely than the other. The stronger the acid, the more ionization, the more of those hydrogens separate, and that's what makes something an acid. So carboxylic acids are weak acids. Those hydrogens don't ionize from every single one of the molecules. Okay, so a lot of information there, but it's just information that you have to remember and be able to apply. So make sure you've made some notes. If you haven't, go back and just write the key points down so that you can use it in any questions you might need. What we're going to look at now is why this is important. So why are we bothered about carboxylic acids? Why do we care about the vinegar that we put on our chips? Now, carboxylic acids are really useful because they help to make esters, and esters have quite a lot of jobs. So when we react, so this is where last lesson comes in, when we react a carboxylic acid and an alcohol, we get an ester. Now, as you can see in front of you, on the left, that is your carboxylic acid. It's shown slightly differently in that it's all 90-degree angles and it hasn't been, but that's just to simplify the diagram slightly so that you can see what actually happens. Now, on the right, you've got your alcohol, and we've flipped it round because it's the OH, so it's the functional group of each of these that does the reacting. Remember, the alkane bit doesn't do anything. It's the functional group, so it's either the COOH in the carboxylic acid or it's the OH of the alcohol that is going to do the reacting. So that's why they are facing each other, because something's going to happen between those two and make our ester. And I've put them in separate colours, the reason being because when we get the names for our esters, it's going to depend on which bit you've used from where, and it'll all become clear in a minute. So there are important bits. So we've got ethanoic acid. You can see you've got 2 carbon atoms and your C double bond or OH. So we've got ethanoic acid and we've got 2 carbon atoms on our alcohol. So that is ethanol. Now you join those, we're going to be looking at these bits here. So the OH of the carboxylic acid and the H of ethanol. Now those two separate from either the carboxylic acid or the alcohol. Those two separate from that and make water. And then what happens with the remaining structures is that these two things then bond together. So instead of having an OH on the end of that C double bond O, the rest of the alcohol has joined. And this is an ester. So we've got that new functional group in the middle. Because if you think back right to the start, we said an ester has a C double bond O with an O and then an R group on both sides. And these are our two in black. There are just our other alkanes that are on the end, and the functional group this time is in the middle. And this becomes ethyl ethanoate. Now, don't worry too much about where we get the names from. We're going to do a lot on that in a second. So, ethanoic acid plus ethanol gives ethyl ethanoate. Now, like we said at the start, any ester will always end in anoate, and the first bit will always have an yl. So it could be methyl, ethyl, propyl, anything of that with an anoate on the end. So the ethyl bit comes from the alcohol, and the ethanoate bit comes from the carboxylic acids. And we're going to do some more practice of this in a second. So here we've got some examples, and you're going to do these for yourself, but hopefully you'll be able to look at my example and look at the colours, because that's going to help you. Feel free to go back to the slide before for your examples, but this time you're going to react methanoic acid and ethanol. Now, if you look at the names and you look at the colours, so the ethanoic acid in the first one forms the second part of the name, but goes first in the structure. And then the ethanol forms the first part of the name, but the last part of the structure. So use those colours and the diagram, and if you feel like you need to go back to the slide previously, please do that and have a go at creating your esters out of these 4 different combinations. So remember that ethanol becomes ethyl, so methanol would become methyl. The ethanoic acid becomes ethanoate, so methanoic acid will become methanoate, and then you put the carboxylic acid first in the structure and the alcohol last, but looking at that functional group in the middle. Once you've got a hang of it, it's really, really easy, but it's just a bit of practice. I'm actually gutted I can't show you this in the lab at the moment, because I love drawing these diagrams, and it's when you work out how to do them, it's so clever, and it's actually something, it's a proper light bulb moment, because it's, people think it's tricky and then you just get it. So we will go over it when we get back to school, because I am a little bit gutted, but give it a really good go, and obviously we're going to go through the answers, but if you can't draw the diagrams, at least write the names of the ester using that one at the top for help. But do have a go at drawing the displayed formulas, because it doesn't matter if you get it wrong, nothing bad's going to happen. Give it a go, and obviously pause the video and then we'll go through it. So let's see how you did. So methanoic acid and ethanol. So remember, the ethanol forms the first part of the name, so it's ethyl, and methanoic acid becomes methanoate. Now let's have a little look at the displayed formula. So the methanoate bit has to come first. So methanoic acid means it's only 1 carbon atom. So you remove the OH and you add your ethanol on, which is 2 carbon atoms, with the oxygen. So underneath, methanol would become methyl. Propanoic acid comes propanoate. So you would have methyl propanoate. Now the propanoate bit goes first, so you need to have your 3 carbon atoms with your C double bond O, and then you're going to add methanol on the end with just the H and the O missing, which has 1 carbon atom, so it would look like that. So we've got our 3 carbon atoms of the propanoic acid, we've just removed the OH, and then we've got the 1 carbon atom of the methanol with the H removed and joined to that oxygen. So moving on, propanol would become propyl. Ethanoic acid, as we know from the top one, would become ethanoate. So propyl ethanoate. So ethanoic acid, as we know from the top one, you can just copy the first part of the top diagram. So you would have 2 carbon atoms with your C double bond O, and then your O coming off from the propanol, which has 3 carbon atoms. And my apologies, that diagram is actually not correct. You need 3 carbon atoms on the bit on the right hand side, so that last hydrogen needs replacing. I will correct that. So lastly, propanol again becomes propyl. Methanoic acid, we know from the second example, comes methanoate, so propyl methanoate. Methanoate bit comes first, so just like in example number 2, you've got a C double bond O just on its own with the H, and then propanol has 3 carbon atoms, so looks like that. So like I said, it's not the easiest thing, but once you get the hang of it, it becomes a lot more easy and you're going to get a lot more confident with it. Okay, so esters then, they've got this C double bond or functional group. So it's not COOH like the carboxylic acid is, it's a COO because it's in the middle with an R group either side. So a common example is ethyl ethanoate. It's often given if you get a question in an exam, that's what it's asked, that generally that's what it's talking about. And that example at the bottom is ethyl ethanoate. You can see the ethyl is the 2 carbons on the right, the ethanoate is the 2 carbons on the left. So esters are made for what we call a condensation reaction. So it's carboxylic acid plus an alcohol gives ester plus water, because remember we got water removed from the middle. Now that's why it's a condensation reaction. Any reaction that loses water is a condensation reaction. Produces water, condensation. Now they've got 3 main uses. So this is why they're so important to us, because they are used in so many things. So we have a look at these pictures. They're used in perfumes. Esters smell nice. When you do this reaction in the lab, it's quite tricky and can be quite dangerous, but obviously you can do it safely. They smell nice. Esters smell nice. But also a lot of them taste nice as well. So they're used in flavourings. They're very fragrant and they taste really nice. Obviously not all of them, you'd never drink them in the lab to taste it, and they're created under special conditions, but things like sweets and beverages and other things, they have esters in them to make them taste nice. And lastly, they're used in biofuels, so just like alcohols can be, they can be burnt to give us energy. So all I want you to do now, the last little task, and I know this lesson's been a little bit longer than the others, I want you to create a table with the words in red, alcohol, carboxylic acid, at the top. And then all those things labelled A to I want you to categorise as an alcohol, a carboxylic acid, or an ester. So don't just write the letter because it'll mean nothing. I want you to tell me what that is referring to. So either copy down the diagram or write vinegar or something like that and get it underneath the correct heading. We'll pause the video now and then we'll go through it, and that'll be the last thing you need to do. So let's go through. So alcohol, we've got the OH functional group. Make sure you're ticking these off, correct them if you've got them in the wrong place. Use a different colour pen just like we would in class, help you out a little bit. So as you can see there, you have got the displayed formula. What I want you to do is name that. Hopefully you can identify that that is ethanol because you've got 2 carbon atoms. And as we know, they are used in alcoholic drinks. That's the main use, but you can use them in solvents and biofuels as well. So carboxylic acid, you've got vinegar. Hopefully you'll remember that it's called ethanoic acid. That's the acid in vinegar, and we can put that on our chips. COOH is our functional group. And when we draw it out, as you can see, it looks slightly different. The reason I put a different way of presenting it in is to show you the different ways it can look. So sometimes we see it completely at 90 degrees to each other. Before we saw the C double bond O and that was at the top. We've seen them on an angle, but as long as you can see that you've got a C with a double bond O and an OH, that's your carboxylic acid. So lastly then, esters. There's your structure. Your ester, make sure you know that you've got that C double bond O and an O and it's in the middle. So C is your ester. Biofuels, flavourings and perfumes are the uses, and you've got COO as your functional group. Now this lesson I appreciate is quite tricky, and this is one of the reasons I've moved on to these kind of delivery of lessons, because it is tricky and I love these lessons and I really wish we were drawing these structures in the lab and we had the whiteboards and the mods out, and we will do that when we return to school because it's important that you can draw these structures and know where they come from. But if you're having massive problems, do email me. Now that's our last lesson of learning for today and for this week, sorry. You're going to have your Seneca lesson as well to do some practice, and then obviously Thursday's lesson will be for you to answer those questions and submit them to me. So I really hope you do. I hope your time in school this week has been really useful. And next week in school, you're going to do a bit more work, based, like questions based, and get some help from your teachers and some feedback on it rather than just having conversations like this week. Let me know if you've had any problems, and thank you for watching and for all your hard work. Keep it up.